Namaste. Welcome to the next video of Machine Learning Practice course. In this video, we'll discuss numeric transformers in the data preprocessing. Numeric transformers are applied on numerical features. There are three types of transformers. The first one is feature scaling, second is polynomial transformers, and the third one is discretization transformers. Let's look at feature scaling. Numerical features with different scales lead to slower convergence of iterative optimization procedures. Hence, it is a good practice to scale numerical features so that all of them are on the same scale. This leads to better convergence of iterative optimization procedures like gradient descent, mini-batch gradient descent, and stochastic gradient descent. Let's learn how to scale numerical features with sklearn API. There are three feature scaling APIs that are available in sklearn: StandardScaler, MaxAbsolute Scalar, and MinMax Scaler. Let's look at them one by one. The StandardScaler transforms the original feature vector into new feature vector by using the following formula. We calculate mu, which is the mean, and the standard deviation, and basically subtract mean from the feature value and divide the difference by the standard deviation to get the transformed value. Let's take an example. We have original feature matrix which has got 5 samples and a single feature. We can calculate the mean and standard deviation from this particular feature column. The mean is 4 and the standard deviation is square root of 2. We first instantiate StandardScaler object and call fit_transform method on it with the original feature matrix as an argument. Again, I would request you to notice this fit_transform and also appreciate the uniformity of the sklearn API. All transformers we are using fit_transform method on the original feature matrix, and this gives us basically the transform feature matrix where each value is transformed according to this particular formula. So you can see that in case of the first value, the value is 4, the mean is also 4, so 4 minus 4 is 0, so we get the value of 0. In case of the second value, this difference is 3 minus 4, which is minus 1, and we divide it by the standard deviation, which is square root of 2, so it is minus 1 by square root of 2, and so on. So you can also see that the remaining values also come from this formula. You can verify that by doing the computation yourself. And note that in case of the transform feature vector, we have mean 0 and standard deviation of 1. So we convert the feature column with mean of 4 and standard deviation of square root of 2 to mean 0 and standard deviation 1. So this is what StandardScaler does to each feature column or to each feature. And recall that this fit_transform method learns parameter mu and standard deviation from the original feature column. That is specifically done by the fit method, and those parameters are actually stored they are stored in this particular object of StandardScaler, and these parameters are used again and again in order to transform this particular feature column in other sets like eval set and the test set. The MinMax Scalar is another way to perform feature scaling. It transforms the original feature vector into a new feature vector so that all values fall within the range 0 to 1. So it achieves it with the following formula. It subtract the value of each feature with it subtract the value of each sample with the minimum value of the feature and divides it by the range, the total range for that feature, that is calculated by subtracting the min value from the max value. So x.max and x.mean are the largest and smallest value of that feature. Of course, this is in the original feature vector. Let's take a concrete example. This is the original feature matrix containing 5 samples, and of course there is a single feature. So before applying the MinMaxScaler, we first instantiate the MinMaxScaler object and call fit_transform method on the original feature set. And this gives us the transform feature matrix with the transform values that are computed using this particular formula, where each feature value is, so from each feature value we subtract the minimum value and divide the difference by the range of the feature. Here you can see that the range of the feature is from -5 to 5. So x.mean is -5 and x.max is 15. So the total range is 20, and you can see that the maximum value is 15, so maximum value gets transformed to 1 because this is 15 minus 5, so this is the numerator becomes 20 and the range is 20, so it's 20 by 20, which is 1. And the minimum value basically gets transformed to 0. And you can again verify that using this formula. So the value is -5, we subtract -5 plus 5, this is 0, so hence it gets transformed to 0. You can also check this, let's say for this value 5, so we have value 5 and minimum is -5, so numerator is 10 and the range is 20, so it is 10 by 20, hence this 5 gets transformed to 0.5. MaxAbsolute Scalar is the third feature scalar, and it transforms the original feature vector into a new vector so that all values fall within range -1 to +1. So here we divide each value of the feature by the maximum absolute value, and maximum absolute value is calculated as max of x.max and mode of x.mean. So x.max, and we also take the mode of x.mean and we calculate what is the max value. So let's take a concrete example here. We have a feature matrix with 5 samples and 1 feature. These are the feature values. You can see that the maximum absolute value here is max of, the maximum value is 5 and minimum value is -100. So we take mode of -100, which is 100. So maximum absolute value is 100. And when we apply fit transform on the MaxAbsolute object, we get the transformed feature matrix, which is with these values. So you can see that the maximum absolute value is 100, and hence this particular value gets transformed to -1. So only difference between the previous scalar and this scalar is that this scalar gets us values in the range -1 to +1. Earlier scalar was getting us value between 0 to 1. So these are some specific feature scaling techniques that we are using. We can also transform the feature using certain transformers like log transform or square root transform or any other custom transformer of your choice. So here the function transformer helps us to construct the transform feature by applying a user-defined function. Let's take a concrete example. Here we have original feature matrix with 4 samples and 2 features. So this is the first feature, the first column represents the first feature, second column represents the second feature. Here we instantiate a function transformer object with a function which is log to the base 2, and then we call the fit underscore transform on this original feature matrix. So what happens is we apply the log to the base 2 to each feature and obtain the transform feature set. So you can see here that this 128 is transformed to 7 because log of 128 to the base 2 is 7. Then the log of 2 to the base 2 is 1, log of 4 to the base 2 is 2, log of 5 and 2 to the base 2 is 9, and so on. So you can also apply this log to the base 2 to each value in the second feature column, and you will see the transformed values which are log to the base 2 of the original values. We have seen in machine learning techniques course why polynomial transformations are important to us. Polynomial transformations help us to learn nonlinear relationship between the features and the label. So we use polynomial transformation to generate a new feature matrix consisting of all polynomial combination of the features with degree less than or equal to the specified degree. Let's take a concrete example. Let's say we have a feature matrix with two features x1 and x2. Let's apply a polynomial features of degree 2. So we instantiate a polynomial features object with degree 2 and we apply fit transform method on this original feature matrix. So what happens is we get the degree 2 transformations here, which is x1 is copied over as it is, x2 is copied over as it is, then we have x1 x2, x1 squared, x2 squared. In addition to that, we also get a value of 1 here, which is the not shown in this particular representation. In the same way, we can apply polynomial features of degree 3. And when we apply polynomial features of degree 3, you can see that we have now degree 3 feature. The maximum degree of the polynomial is 3. So you can see that the features here are x1 and x2 are copied over as it is. There will also be 1 which is copied over by default. So there is 1, x1, x2, then the combination x1, x2, x1 squared, x2 squared. Then we have the third order features x1 squared, x2, x1, x2 squared, x1 cube and x2 cube. So you can also see that degree 3 polynomials has all the features from degree 2 polynomials and additional features from the third degree. So we have this polynomial features transformer that can be used to convert the original feature matrix into a polynomial of desired degree. Then there is KBinsDiscretizer that divides a continuous variable into bins, and each bin is represented with one hot encoding or with ordinal encoding. Let's look at a concrete example. Let's say we have a feature matrix with 9 samples and one feature, and these are values for that feature for each of the sample. Let's say we decide to use KBinsDiscretizer with number of bins equal to 5. We want to split these bins uniformly and we want to use, let's say, ordinal encoding. So what happens is the entire range is split into 5 different parts, and based on that the transform features are calculated. So you can see that since the range is between 0 to 1, there is we can make 5 bins with thresholds of 0.2, 0.4, 0.6, 0.8 and 1, and you can see that values that are less than 0.2 are transformed to value 0. So these first two values are transformed to value 0. Then we have values between 0.2 to 0.4 transformed to 1, 0.4 to 0.6, there is only one value which is transformed to 2, 0.6 to 0.8 is transformed to 3, and 0.8 to 1 is transformed to 4. So this is how K-Beans discretizer works. Sometimes we have need to convert the numerical features into such kind of discrete features, and K-Beans discretizer will help us perform that transformation.